I'm here. Thank you. All right, folks, I'm going to drive the point home one more time about the geometric interpretation of everything that we've been talking about in terms of Fourier series. So here was our story. We had Fourier series. We're still in continuous time. I'm going to make our move into discrete time sometime later in this lecture. We have a signal, x. We want to represent it as a linear combination of a bunch of functions. And I'm deliberately using the notation that you use for vectors. I'm keeping the n dependence out of the picture for now. Okay? So these are the coefficients of the linear combination. Linear combo. And these, the CKs, are a bunch of mutually orthogonal or perpendicular vectors. We're expanding our horizons in this class. We're generalizing what we understand a vector to mean. And we're looking at signals as vectors. They're orthogonal, so that means that when I take any two of these vectors, and I project one onto the other using this notion that you've now seen several times, inner product, what do I get when k is not equal to L? When I'm looking at two different vectors in that set, I get 0. Okay, that's our basic picture. Figuratively speaking. And the analogy I drew with Cartesian vectors was that you have a couple of vectors like so, C0 and C1. They're orthogonal. And our goal is to represent an arbitrary vector x in that plane in terms of a linear combination of these two. So we want to represent x as x0, c0 plus x1, c1. Well, it's easy to say I want to represent this as a linear combination of these two. The main question is, how do I find those coefficients? There are actually a couple of issues here. One is, do I have enough of these CKs? How many do I need if I'm living in two-dimensional space? 2. I need 2 of these that are orthogonal to each other. So I know my set, as far as this picture is concerned, requires only 2 of these vectors. Any vector in two-dimensional space can be represented as a linear combination of 2 orthogonal vectors. So I don't need a third orthogonal vector. In fact, you can't find a third orthogonal vector, or a third vector that's orthogonal to this and to that. So in terms of my accounting of the number of vectors I need, I'm all set. Okay? The remaining question is, how do I find x0 and x1? How do I know how much of C0 I have to add to how much of C1 to make my soup? Okay? It's kind of like a recipe. A teaspoon of this, a quarter teaspoon of that. And that's where this notion of inner product, the notion of projection, came into the picture. So with your guidance, in the previous 2 lectures, we took the projection of this vector x onto each of these individual vectors to find out how much of each we need. And that projection was this much of the C1 vector over, well, it happens to be just about 1 times the C0 vector. So the projection onto C0, now I'm running out of colors here. Sorry about that. This vector will be what? Can you give me a symbolic representation for this vector? What is that vector? x1, c1. So I take c1, I multiply it by x1, and I get that vector. And this yellow vector here, why am I running out of colors? I thought I had a purple. You feel like you're in the kindergarten? I also give stars to the students. Here we go. The problem is this purple is not quite purple. So this one is x0, c0. Okay? This process of projecting this vector onto each of these orthogonal vectors is done by that inner product. So we took the two sides of this equation, and we said, okay, project x onto C0. And on the right-hand side, I've got to do the same thing. x0, C0 plus x1, C1, projected onto C0. These two are numbers, and the way we've defined inner products for vectors allows us to simply take these numbers out. So first of all, I have to deal with the summation. So I have x0, C0, projection onto C0, plus, that's where this plus is, x1, C1, project onto C0. And now I have these two constants that I can just take out. So I have x0, C0, C0, plus x1, C1, C0. Okay? What can you tell me about this second term? Why? Because they're orthogonal. We've already said they're perpendicular. So when I project one onto the other, when you take the projection of this red vector onto the yellow one, or vice versa, you get 0. There is no projection of this onto that. I need 0 of this to construct that. So that's 0. And what's the solution now to x0? Talk more! Talk more! Inner product of x and C0. C0, C0. This is one of our magic equations. And if I were to ask you, tell me the next coefficient, what would you do? Are you going to go through this process again? You better not. You're going to run out of time on the exam. X1 is? You project x onto C1 this time. C1, C1. For real valued vectors, the inner product is what you're used to from high school. So C1, actually, let me do it with generic symbols. Inner product for real valued vectors. Let's say I have two vectors, f, and I'm living in two-dimensional space. So f has f0, f1 as its components, and I have another vector, g, which is g0, g1. The inner product for real valued vectors is what you know from high school as the dot product. So this is the same as Mr. Trigonometry, no, Mr. Linear Algebra. Wrong class. Linear Algebra's 5th period class, where he talked about the dot product. So that was what? F transpose G, which was you make this into a row vector, F0, F1, and you multiply it by G0, G1. So you get the product of the first components in the next component. And if the vector is larger, then you can continue on with the other components. So the way I've drawn this figure, C0 is the vector what? 1, negative 1. And C1 is what? 1, 1. So tell me what the denominator is for each of these vectors as I've drawn them. 2. So C0, C0 is 1, negative 1 times 1, negative 1. You get 2. And C1, C1 is 1, 1 times 1, 1. You get? Who was it? Let me get my gun. 2. So in this case, the two vectors that I've picked to be the orthogonal vectors that I use to linearly combine and construct any other vector in the class happen to have the same length, and that's convenient. In fact, throughout our discussion of Fourier series, this will be the case, that the vectors we pick that are mutually orthogonal are going to have exactly the same length or magnitude squared. This is the magnitude squared of C0, and this is the magnitude squared of C1. Okay? And what's a good, this looks like 4, let's see, 1, 2, 3, 2. Let's say this is 3, 2. So what's the inner product of x with C0? Figure that out, and figure the inner product of x and C1, and tell me what it is. And if by this time in the semester you still don't know your neighbors, you and I have some chatting to do. So make sure you introduce yourselves. Believe it or not, I still get students in my office who don't have study groups. I don't know what they've been listening to for the semester. Are you ready for Meatball to call on you? Meatball, where are you sitting? There you go. Do your thing. See, that requires them to count the number of rows. There's only one red sweater. Well, actually, no, there's more than one. Don't you love it? When you pick somebody, they always look around. Your name is? Sean. Do your magic, Sean. Louder, louder. The real value. So X transpose is 3 and 2. Shh. Only Sean speaks. 1 and negative 1. And what does that give you? 1. And let's skip to the end for this one. What's the answer? 5. So if I were to ask you, write X as a linear combination of 1 and negative 1 and 1, 1, what would you give me for coefficients? This would be x0, right? And this would be x1. So what's x0? John, are you working it out? What was the formula for x0? See, a whole bunch of you guys came to my office, and one of the things I told you about this class and technical subjects in particular is that when you want to study or learn the material, it's not sufficient for you to look at me or watch me solve 500 problems before you. And then when I put the 501st problem, you'll get stuck. You actually have to roll up your sleeves and do it as mundane and menial as it may seem, because that's what's going to make you efficient with the computations, and it'll make it sink in. So x0. I've given you the formula. Where is it? Right there. John, right there. So what have you got in the numerator? 1 over 2. And x1? 1 over 5. No. 5 over 2, sorry. I went on cruise control there for a minute. So I've got 1/2, 1, 1, plus 5/2, 1, 1 minus 1 and 5/2 of 1. 1, 1. So he makes 1/2 pound of 1 minus 1 and 2.5 pounds of 1, 1. And you get your chicken that will then cook good. Sorry, you wouldn't know Julia Childs. I just carbon dated myself. Now, so this is all review, right? The same discussion can be applied to, well, that's not the vector I want. What was our vector? 3, 2. 3, 2, 3, 2, 3, 2, a periodic signal that has period 2. So this is 0, 1, 2, 3, and then the same story on this side. We said we can use the same principle when we look at periodic signals in discrete time, because when I look at a periodic signal in discrete time, in this case I've drawn a periodic signal with period 2, I can stack up the values of that signal in a vector that I call x, 3, 2, exactly like the vector I have there. And all the information about the signal is embedded in this vector. There's no additional information that the rest of the periods give me, that this doesn't give me. So everything is distilled. So if I can represent x as a linear combination of two other signals that two other signals, C0 and C1, such that C0 is what? That's your turn now. Huh? 1 minus 1. 1 minus 1. So this is 1 minus 1. And it's periodic with period 2. I'm living in a universe of periodic signals with period 2. When I add two such signals together, I get yet another signal in that space, in that universe. So this is C0. And C1 is what? I should label these. 1, 1. 1, 1. 1, 1. This one ends up being a constant signal. That's 0, 1, minus 1, minus 2, and so on. You get the idea. The goal is to split the signal x, or decompose the signal x, into a linear combination of these two signals. And the way we did that was using an analogy from geometric concepts that you knew from high school, that we now generalize to include signals. You didn't study signals in high school. Well, most of you didn't anyway. We use the same geometric concepts to study decomposition of signals. That's what Fourier series expansion is about, except I haven't put the more complicated C0s and C1s in here yet. Fourier series expansion says, instead of these signals, C0 and C1, I want you to write x as a linear combination of CKNs, where these CKNs are these strange-looking creatures. That's where we now depart from our comfort zone of high school linear algebra. Because now we're dealing with CKs that are no longer real valued. Omega naught, you recall, was 2 pi over the period. This is called the fundamental frequency. And this was the fundamental period. So we've got to change one of the major components of our analysis, which is the definition of the inner product. So inner product for complex valued vectors. What did we say it was? The same f and g, now they're complex valued. What is the inner product of f and g? F transpose times g conjugate, which is f0, f1. I'm doing it for 2 dimensions. G0 conjugate, G1 conjugate. So it's F0, G0 conjugate, plus F1, G1 conjugate. The special case that we worked out up to this point was for p equals 2. Notice what happens to these CKs when p is equal to 2. P equals 2. Omega naught is pi. So Ck of n will be e to the I k pi n. And if I'm living in the universe of signals that are periodic with period 2, how many of these CKs do I need? 2. So I need C0 and I need C1. C0 is when I plug in k equals 0. What do I get? 1. So when I look at it as a vector in 2 dimensions, whoops. When I look at it as a vector in 2 dimensions, I get 1, 1. And when I look at this as a vector in 2, well, what is this? K equals 1. E to the I pi n, which is what? Negative 1 to the n. And when I look at that in 2 dimensions, I get 1 minus 1. The moment I go to higher periods, p equals 3, these vectors become complex values. And that's why I need a better definition of the inner product. Okay. One thing that I kept promising I would do, and I just didn't get to by the end of last lecture, was to show that when I have Ck defined in this way as a complex exponential, and I look at another one with another index, e to the I L omega naught n, that these two are actually mutually orthogonal. K not equal to L. When K is not equal to L, we want to show that these two are orthogonal. Actually, I did show. Yeah, Brian was happy at the end of last hour. Yeah, we did show this. But let's go over that again, because it's important. It involves certain techniques that keep showing up over and over again in the kinds of problems that we do. So I want to take the inner product of these two. Fine. Ck, Cl is what? Brian, you do it. Say Ck. Now I'm not restricted to p equals 2. Okay, so Ck will be C0 all the way to, I'm sorry, Ck0 all the way to Ck p minus 1. So in general, it will be a vector with p components. And Cl will be similarly defined. So summation from that would be summation over n or k? Huh? N. From 0 to p minus 1. Ckn conjugate and so this is just a component by component multiplication of the two vectors Ck and Cl, which I haven't written out in full detail and glory. L p minus 1. Okay? And so what do you get? N equals 0 to p minus 1. E to the I k omega naught n times parentheses. So when you multiply those, as an inner product, you have e to the I k omega naught n times e to the minus I L omega naught n. And I merge those two, and I have this expression. One of the things I told you last time was that whenever you have a sum or an integral involving some kind of an exponential that may potentially be 0, you always have to separate the two cases, where the exponent is 0 and when the exponent is not 0. Go back to the other side. Okay, so CK, CL. I'm going to consider two separate cases. When is the exponent 0? K equals L. If K equals L, the inner product would simply be the summation of n from 0 to p minus 1 of what? 1. And what's that answer? P. What this essentially means is that CK equals P. Remember I told you it's convenient to have the magnitude squared of each of these vectors be the same, regardless of the index. Well, that's happened here. What this means is that the magnitude squared of CK is P. That's great. And what about the other case? Well, let's write it out again. But this time, I'm going to write it this way. It's some alpha to the nth power, and I'm taking the summation. So it's a power series, finite power series. And this is where we have to do a bit of a review. And you need to have these in your cheat sheets, what I'm about to say, because it pops up over and over again, and you don't want to have to derive it and rederive it on the spot. It's great to be able to do that. You just don't have that kind of time on an exam. So when you have a summation from A to B, where these are integers, of alpha to the n, the way you find out if you forget and you don't have it in your notes is you let that summation be equal to some value s. Okay? And you write out all the terms. So you have alpha to the A plus alpha to the A plus 1 plus alpha to the B minus 1 plus alpha to the B. Okay? If alpha is not equal to 1, you can multiply both sides by alpha. And what do you get? Let me put the equality sign here. If I multiply both sides by alpha, what happens? Well, alpha to the A plus 1 plus alpha to the B plus alpha to the B plus 1, right? What happens when you subtract the top equation from the bottom equation? Subtract the top one from the bottom one. What do you get? Alpha minus 1 times s. And on this side, what do you have? What happens to all the terms? Huh? A whole bunch of these cancel. And this cancels with that. Everything in between these two cancel with everything in between these two. And what are the only two terms that are left? Alpha to the? You need to be a little louder. Alpha to the? No, I'm subtracting this from this guy. b plus 1 minus alpha to the a. Whoever comes after me in this class is going to hate me. These chalks. I turned the blackboard into a whiteboard. Oh. So alpha minus 1. S is alpha to the b plus 1 minus alpha to the a. And remember I said alpha is not equal to 1. So as long as alpha is not equal to 1, I have a value for the summation. Alpha to the b plus 1 minus alpha to the a over alpha minus 1. So we have a formula for our finite sum. N equals, what's the deal with this chart? N equals a to b, alpha to the n, is alpha to the 1 plus the top number minus alpha to the bottom power over alpha minus 1. Okay? This is what I want you to have in your formula sheet. I don't want you to have to derive it on the spot when you're under time pressure. So let's apply this to our complex exponentials. What's the alpha in our complex exponential story? E to the k minus L omega naught. And how do you know that alpha is not equal to 1? K is not equal to L. So we know that the exponent is not 0, and that's why. Well, it's not just that. There's one additional feature that we know. Because notice, if K minus L is equal to P, what happens? What happens when K minus L is equal to P? What if? Then you have e to the I p omega naught. And what do you know about p omega naught? It's 2 pi. And that's equal to what? 1. So what is it that guarantees that k minus L is not equal to p or some integer multiple of p? Huh? Well, yeah. So we're only looking at C0, C1 through Cp minus 1. The set we're looking at has indices that are no farther from each other than p minus 1. And that's why we're guaranteed that this is not the case here. So we're guaranteed, I should put this in red. Not the case for us. Now let's go back up there, apply this formula. In fact, I'm going to have you do that. Talk to your neighbors and make sure you get that number and tell me why. What is it that you want that number to be? You want that number to be 0. So talk to your neighbors and figure out why that number is 0 based on the finite sum formula that I've given you. Then we'll take a break. Sean, you get to pick the next person. Who's your victim? Ryan. Go for it, Ryan. E to the I, k minus L times P times omega naught minus 1. And what can you tell me about the denominator? Should I even care? If I'm trying to prove that this summation is 0, and I've already established the conditions under which alpha is not equal to 1, then all I have to show is that the numerator is 0, because I'm guaranteed that the denominator is not 0. I'm guaranteed that. So, I don't know and I don't care. Okay, Ryan. What about this numerator? P, so this, by the way, this concept is something you'll be using over and over and over again in various problems in different forms and contexts and shapes. Omega naught, the fundamental frequency, is defined as 2 pi over the period. So omega naught P is always 2 pi. Okay? So I plug in 2 pi there. E to the I, k minus L, 2 pi minus 1 over I don't care. K minus L is an integer. The first term is always 1. K minus L is an integer. Therefore, e to the I, k minus L, 2 pi is equal to 1. And that makes the numerator 0. So now we've shown that when I take the inner product of ck and cl, as long as k and l are different, and as long as I'm looking at a set over a range of indices that go no farther than p, I'm guaranteed orthogonality. So ck cl is equal to 0 when k is not equal to l. There is a way to summarize all of this, or this result between the ck's, using Kronecker deltas. Can somebody tell me what that is? If I want to write this for the most general case, whether k is equal to L or k not equal to L, I want to include both cases in one simple expression. How would I do it? Delta k minus L times P. It summarizes all the stuff that we've written. The inner product of ck and cl is non-zero only when k is equal to L. If k is not equal to L, what's on the right-hand side? Huh? 0. And when k is equal to L, this delta is 1. And what do I have to put in front of it? P. So that's a summary of the situation between these vectors. So this is an overview, a review, whatever you want to call it, of everything we've said so far about discrete time Fourier series expansion. But it's important not to lose track of what it all means. We're saying x of n is a linear combination of a bunch of these complex exponentials. And that linear combination involves how many terms? P. What did you say? Saved by the bonsai. Okay. No, we already had our break. We didn't have our break? That was a working break? Get to it. You guys are slacking. You need to stop me. I got to get back to it. Talk to me after class. Okay, folks. Let's reassemble. Now, I've said this tall tale over a couple of, or now 3 lectures. The most important thing in this whole story is how you interpret the equation that we've arrived at. So actually, we have 2 equations. The other equation is x inner product with ck. We found the formula for it. Over ck. This is the equation that gives us the coefficients. And ck is what? P. So you have a 1 over P. And x inner product with ck is what? Summation n equals 0, P minus 1, x xn ck star. Right? That's the inner product. So it's 1 over P, summation n equals 0 to P minus 1, xn. And what's ck star? E to the negative. One of these exponentials is negative. In our story, it's going to be in the equation that involves the coefficients. Negative k omega naught n. Okay, these are the 2 main equations that we've arrived at. We said this is the synthesis equation. It's the equation that tells you how to synthesize the signal x from a bunch of complex exponentials. And this is called the analysis equation. It's the equation that tells you how much of each of these frequencies is present in this signal. And this is where we walk into the interpretation zone. What does all this mean? Well, let's look at the synthesis equation. The synthesis equation says you've got a signal, you've decomposed it into a combination of complex exponentials, but these are not arbitrary complex exponentials. X consists of, what this equation says is that the signal x consists of a finite set of frequencies. And what are those frequencies? What are they? Lowest one. 0. Omega naught. 2 omega naught. P minus 1 omega naught. In other words, a signal that is periodic with period P cannot contain any frequency other than this set. Now, some of these frequencies may be absent from our signal. That's possible. How do you know if a particular frequency, let's say omega naught, doesn't contribute to our signal? How do you know that? The corresponding coefficient will be 0. And that's where the next part of the interpretation comes, which is that associated with each of these frequencies is the coefficient in our expansion. And the coefficients tell you how much of that frequency is present in the signal. So I say here, what's a good way to put it? A measure of how much the frequency k omega naught contributes to the signal, contributes to x. Let me emphasize this is the frequency. So each xk, the kth coefficient, tells you how much of the kth frequency is present in the signal. Okay? So if a particular xk, let's say x1, happens to be 0, that means omega naught just is a frequency that's not manifested in the signal. The signal does not contain that frequency. Any questions on this interpretation? This is very important. Yeah. Ahmed. So Mohammed's question is, are we saying that there's zero contribution from frequency 0? What's the answer? What does this mean? There's x naught amount of contribution by frequency 0. I didn't say x0 is 0. Right? x0 is a coefficient. Each of these is just a coefficient. They may be complex valued coefficients, and in general they are. So it's actually the magnitude of each of these that tells you how much of the frequency is present. But x0 I never said was 0. If x0 happens to be 0, yeah, then 0 frequency. Then the signal has what? What does 0 frequency mean? The DC value of the signal is 0 if x0 is 0. Can you tell me how x0 is related to the signal? That's actually a good exercise. What does the analysis equation tell you about x0? x0 is a very special coefficient. It's the offset. How do you get that? What is it in terms of the signal? It's frequency 0. Yep. You're all on the right. I want the equation. 1 over summation x0 plus x1 plus x p minus 1. What does it mean for me to add up all the values of the signal over one period and divide by the by the period? This is the average value of the signal over one period. Average value of x over one period. So if you're looking at a periodic signal and it spends as much time above ground as below ground, its DC value is 0, and you can immediately tell me what the x0 coefficient is. Right? So if I tell you, this is my signal. 3 minus 3 halves minus 3 halves. Again, minus 3 halves, 3, minus 3 halves, minus 3 halves, 3, minus 3 halves. What's x0? 0. I don't want you to spend time writing equations. And you gain this kind of intuition with practice and with paying attention to rereading your lecture notes, watching the webcasts, rewatching the webcasts, rewatching the webcasts. Until you get to the proper understanding of what these coefficients mean. In particular, this one. You're looking at a periodic signal with period 3. So each segment is of length 3. And when you look at one period, you add up all the values. 3 minus 1.5 minus 1.5 is 0. So the average value of the signal is 0. It spends as much time above ground as it does below. And so its DC value by inspection is 0. Xn is usually a signal you come across in real life. It can be your heartbeat, EKG signal. It can be a lot of signals are periodicity is all over nature. So that's a signal that you're given. And it's typically real valued. Not always, but typically real valued. No, X you draw on an axis of n. Yeah. But you can't draw these in an axis of n. They're complex valued. So, no. The way you see the decomposition is by looking at the coefficients. Those will be complex numbers in general. Again, not always, but in general, they're complex numbers. And their magnitudes will tell you that the contribution of each frequency to the signal. So if the magnitude of x0 is very large, and as you go up in the k index, the magnitudes decrease, what kind of a signal is that? It's low pass. It's got most of its energy content around 0. And as you go higher and higher in frequencies, the contributions of those frequency components decreases. And so it's a relatively smooth signal. The faster the signal varies, the larger the magnitudes of the higher coefficients and the smaller the values of the lower coefficients. So there's a direct relationship between how the signal behaves in the time domain or along the n-axis and what those frequency coefficients tell you. Yeah.
So since the complex exponential has a geometric interpretation when you compress it, right? Shouldn't we also be able to look at xn in the complex form?
Well, the problem is you can't. It does, for continuous time, it's very simple to draw. In fact, we had that Java applet where the rotating phasors were rotating, and you had a whole bunch of these rotating phasors adding on top of each other according to a linear combination to construct a periodic signal. And in the first lecture after, this is our last lecture this week, right? In the first lecture after Thanksgiving, I'll bring back my computer, and we'll see the Java applets. I haven't moved into continuous time yet. That's what I was hoping to do today. I'll probably make my entry into continuous time. But yeah, there is certainly a geometric interpretation. These complex exponentials are phasors. It's just that trying to do this dynamically in terms of time is clumsy because there's a discrete jump in time, right? The phasors go from... But in continuous time, they flow and they rotate continuously, and it's got a very nice interpretation. Okay. So we've done some, yeah. I am going to have office hours, but I am going to have office hours for this problem. It's going to be it's due next Tuesday, so next Monday night. Monday night we'll have the party. I made sure you stay on the ground during Thanksgiving break. Hey, at least I didn't make it due on Monday. Okay. Are you ready now to move into continuous time? Here's the story with continuous time. In continuous time, we have periodic signals of various forms. So here is a triangular waveform. This is one period. Let's say this is between, I'll put the axis, the origin of the timeline smack in the middle of the triangle. And let's say the peak values are 1. The main distinction that enters the picture when we move to continuous time periodic signals is that even though I'm looking at a finite interval, the number of signal values in that interval is infinite. In fact, it's not just an ordinary infinite number. Not all infinities are equal. Some are more equal than others. I have an uncountably infinite set of points in one interval. So a main distinction with discrete time is that we have an uncountably infinite set of points in one period. And this is what got Doc Fourier at the end of the 19th century in trouble. Because Fourier said you can write this signal as a linear combination of a bunch of complex exponentials, where that linear combination now goes from minus infinity to infinity. Something is counterintuitive about this whole picture. I have an uncountably infinite set of points in one period. Your intuition would say, well, I need an uncountably infinite set of coefficients and an uncountably infinite set of these complex exponentials, or CKs. But that doesn't happen with this story. You're in an inquisitive mode today, Ali. Lowercase what? It is a lowercase t. Somebody needs a Thanksgiving break, huh? Is that a small enough t for you? So, the counterintuitive part of this whole story is that even though when I look at my signal, I have an uncountably infinite set of points in one period. There's a continuum of values. Fourier claims that I can represent that signal with a countably infinite set of functions CK. And Fourier, being a physicist, was mocked at, laughed at, and given a hard time in this convention that he attended with not very sympathetic mathematicians. So it took a while before this idea was accepted. The trick is this. This equality is not it's not equality in the ordinary sense that you're used to seeing. This is, in general, not a pointwise equality. It does not say that the right-hand side is at every single point equal to the signal x. It does not mean that. For certain signals, it happens to be so. But in general, it does not mean that when you construct this linear combination, you're going to get, on a point for every value of t, exactly the value that you have on the left-hand side. In particular, you run into trouble when you have discontinuous periodic signals, like the square wave that many of you have seen in E40. It shows up all over the place. This is the square wave. So this is 0. This is p. This is minus p. Whenever your signal has discontinuities, this cannot, it's very obvious why this is not a pointwise equality. Because what you're looking at on the right-hand side is a perfectly infinitely differentiable function. Each of these exponentials is infinitely differentiable. You know that already. It's smooth. Whether you plot the imaginary part or the real part, it's smooth. The imaginary part is a cosine. The imaginary part is the imaginary part is a sine, and the real part is a cosine. So each of those is smooth, and you're linearly combining a bunch of smooth functions. You're not going to get a discontinuous function. So what happens when you actually construct this and plot that on the same axis? Well, it ends up being, if the higher and higher the number of terms that you pick. Obviously, in real life, you can't have an infinity of terms. There's no computer, no device that can hold an infinity of coefficients. So you've got to chop it up at some point. So let's say I go from minus 100 to 100. Okay, just for the sake of argument. Then I'm going to get this ringing effect near the edge, and then it goes down. At the discontinuity, it passes the halfway point. It ends up being that way. It's not at all obvious why it's so. And we're not going to really belabor the point in this class. But I'm just mentioning this, that this equality is not pointwise, and this equation should be understood not in terms of pointwise equality. So, but let's suppose that this is accurate. So from another perspective, you have an infinity of terms. That's nice. You're not claiming that a periodic signal can be represented with a finite number of these complex exponentials. But there's still something very special about periodic signals, even in continuous time. What are the only frequencies that are present in these signals? 0, omega naught. What about the other side? Plus minus omega naught, plus minus 2 omega naught, plus minus 3 omega naught, all the way up. Okay? So if I'm looking at a periodic signal of period P, there's no way that's going to have any frequency component at frequency, say, omega naught over 2, or 3 omega naught over 2. The only frequencies that can contribute to that signal are these integer multiples of the fundamental frequency. And so this harmonic effect is again manifested. Harmonics of omega naught, meaning integer multiples of omega naught will contribute to the signal. What the coefficients are? Next Tuesday. What was that all about? Hey, you should have encouraged me like this all throughout the semester. Have a great break.